Hello, future teachers. Welcome to your Friday pre-recorded lesson. We are going to be looking a little bit today at the process of exponentiation, trying to explain that, find some of the properties of exponentiation, and then hopefully eventually dive into some of the ideas around working with exponents and integers as well, which tends to trip up some people a little bit. So I'm hoping that it's mostly a review for you guys and maybe just seeing a couple different ways of how to algebraically prove some of the properties. All right, so this will, I think, be our last chapter inside the integer section, which is kind of exciting. So next week we'll start chatting about a final kind of assessment for these last couple sections. So essentially, I want you to think about exponentiation as an operation that we can do with two numbers. It's similar to addition, similar to subtraction or multiplying or dividing. There are two numbers involved. We have two inputs essentially, and there's going to be one number that's going to be our output. So we have two numbers involved in an exponentiation kind of equation. So let's look at something like 3 to the power of 4. This would be 3 times 3, which is 9, times 3, which is 27, times 3, which is 81. And so the two numbers that we want to be thinking about are the numbers 3 and 4. 3 we call the base of the expression, and 4 we're going to be calling the power or the exponent of the expression. My personal preference is to call the smaller number up top the power, and then you can call the process of finding the number 81 exponentiation. So exponentiation is, I would say, more like a process of how to find your result. And one of the easiest ways as you're starting to introduce the idea or the concept of exponentiation is to think about exponentiation as repeated multiplication. So you even saw me thinking about 3 to the power of 4 in that following way as I was evaluating what this was mentally. So I first went, what is 3 times 3, which is 9. Then I multiplied 9 by 3, and then to get 27, and then I multiplied 27 by 3, and I know that that's 81. So the base and the power tell us different things with regards to this representation of thinking about exponentiation as repeated multiplication. So the base tells us some information, right? The base essentially tells us what number is repeated inside of the string of multiplications that we get. And the power essentially tells us how many times to repeatedly multiply something. And this doesn't always work. I mean, there are instances in which we try to write an exponential kind of thing, and it's not as easy as thinking about it as repeated multiplication. But for the most part, working inside of middle school, where we're going to be seeing exponentiation a lot, I think it's fine to think about it as repeated multiplication. But like I said, you eventually are going to get yourselves into like, how do I think about 3 to the power of 1.5? Is that like 1.5 multiplied copies of 3? Like how do I think about that? Or even worse would be something like 3 to the power of pi. What the fuck does that mean, right? How many times do I actually repeat this multiplication? Is it I multiply 3 out 3.1415 times? Right? So eventually this idea will break down, and it doesn't always make sense to think about exponents as repeated multiplication. But I think when you're introducing, it's a good kind of fallback concept to think about. It's a good initial representation. So let's just maybe quickly skirt through a couple of properties of exponentiation. I'm going to do my quick here, do my best to kind of keep this brief. I don't want to spend too much time doing this because I'm hoping that most of you know a lot of these properties anyway. So we're just going to label these in a numerical kind of order. I'll try to give a numerical example over on the side. And our first property is that if we have similar bases and we're multiplying similar bases together, then we can actually combine the bases by multiplying the exponents out. So this is a to the power of m times a to the power, I'm really struggling getting the second m, there we go, a to the power of m times a to the power of n is equal to a to the power of m times n. So in green, I'm going to come through and give a numerical example of how this might work. So let's say we had 7 squared times 7 cubed. Now, the property says I should be able to write this as 7 to the power of 2 times 3. Now, why is that the case? Well, if we look at this first 7, which is 7 squared means multiply 7 by itself 2 times. Okay, and then this second 7 cubed, says multiply this 7 by itself 3 times. So there's 7 cubed. And notice altogether we have 1, 2, 3, 4, 5. Oops, sorry, this should be a plus sign. This should be m plus n, not m times n. Try again. Because when I go in and I look at how many copies I have 1, 2, 3, 4, 5 copies of 7. So in other words, I started with 2 and 3. My end result is 5. This 5 comes from adding together the 2 and the 3. So like I said, make sure you just make that small fix up here. This should be a to the m plus n. Second property is that if I have an exponential expression inside a set of brackets and I go to raise that to some power as well, what I can do in this case is actually multiply the powers. Okay, so this is where the multiplication of powers comes from. It comes when I raise an exponential expression to another power. So let's keep on working with our 7s, 2s, and 3s here. And let's say maybe we have 7 squared 3 times. So what we're going to do is we're going to interpret this number 3 as the base multiplied by itself 3 times. So I'm going to think about 7 squared as the base, so that when I go to expand this out, I get 7 squared times itself 3 times. So I get 7 squared times 7 squared times 7 squared. And we know from the first property now that this should be 7 to the 2 plus 2 plus 2, Or if you needed to, you could expand this out even further and see that you do have 6 copies of 7. But by property number 1, we know that this should be 2 plus 2 plus 2, which is 7 to the 6. Okay, so we've shown that 7 to the 6, which is our final answer, is really like 7 to the 2 times 3. So that's the second special property of exponentiation. Now the third property deals with division. So if I have a very similar looking base, but maybe I have different powers here in the exponential expressions, if I'm dividing those like bases, I am permitted to subtract the 2 powers. So again, maybe let's just kind of stick with some 7s here. So let's do like 7 to the 5 divided by 7 squared. Okay, so 7 to the 5 divided by 7 squared. Now, I think about this from the standpoint of, I know what 7 to the 5 looks like. That's 7 multiplied by itself 5 times. And I know what 7 squared looks like. That's just 7 multiplied by itself twice. And so what we can do now is we can start canceling out common factors. So for instance, this 7 and this 7, these would divide and give me the number 1. This 7 and this 7, these would also divide and give me the number 1. So what I'm left with is 7 times 7 times 7, or 3 multiplied copies of 7. Okay, and you can now see that relationship between the 5, the 2, and the 3. Okay, so in other words, I start with 7 to the 5 divided by 7 to the 2. It's really like saying 7 to the 5 minus 2. One other important property I particularly like is this idea of being able to distribute a power through to bases that are multiplied together. So this does only work for, I have to maybe write this in red, this only works for bases that are multiplied together. It doesn't work if the bases are added together, unfortunately. And we'll take a look at that case in a second. But what this is saying is it's possible to take this power and distribute it over the multiplication. So a power does distribute through multiplication. So think about it in that tiered system, right? When we were kind of like looking at expressions like this, we knew that multiplication distributed over addition. So the higher tier operation distributes over the tier that's one below it. And it's the same thing here. Exponentiation is able to distribute over the tier that's below it, which is multiplication. So exponentiation does distribute over multiplication in this very special way. So if I had something like a couple different bases, like let's take 7 and 5. And let's say I had some kind of power out here that I wanted to work with. So maybe I had 7 times 5 to the power of 3. And I don't want to turn this into 35 to the power of 3. I want to keep it as 7s and 5s in this maybe instance because 7 and 5 are prime numbers, right? So maybe it's helpful for us to have a factored form. So we can think about this, number 3 up here, as 3 multiplied copies of the base. So again, I'm thinking about this as the base. And I'm interpreting that exponent as I'm going to take this base and I'm going to multiply it 3 times. And because multiplication is commutative, I can drop these brackets, I can move stuff around because we have just a big old string of multiplication. So maybe I can move all the 7s together, and move all the 5s together. And then I can see that I really have 3 copies of 7, and I have 3 multiplied copies of 5 as well. So just interpreting this as I normally would with that repeated multiplication way of thinking, I think that answers a lot of questions with regards to exponents. So if you're unsure of the properties, you can always just interpret this as you normally would, and you just have to know that we think about exponentiation as repeated multiplication. If you're happy with that, most of the answers just kind of come forth by thinking about it that way. If you happen to know the properties, it just speeds up this process of expanding out and simplifying. That's essentially what it does. Okay, if I happen to have a fraction to some kind of power, it is possible to distribute over a division as well. So exponentiation, my apologies, will distribute over division as well, just like it'll distribute over multiplication. And it distributes in the way that we kind of expect it to. The numerator gets the power of m as well as the denominator. So let's just swap up our numerical example a little bit, and we'll write 7 over 5 all to the power of 3. And so what happens in this case, if I think 7 over 5 as the base, if I interpret this number as the base, then the power of 3 is telling me to multiply this base 3 times. Okay, and multiplying these fractions out, I'm going to multiply all the numerators, I'm going to multiply all the denominators together. No, we haven't specifically talked about fractions yet, but I'm hoping that some of these operations are familiar to you at least. So multiplying these fractions together, we get 7 times 7 times 7 in the numerator, so that's 3 copies of 7 in the numerator. We get 3 copies of 5 in the denominator, and there's our distribution property via example. Okay, let me just check. That one we definitely should do. Okay, here's the one that's a little bit tricky to think about, but we can hopefully sort this one out. Let's interpret what we mean by a negative power. I think this is a little bit tricky. So I know what a to the positive m is, right? So we know a to the m looks like a times a times a times a, and this should happen m times. But what about a to the minus m? What does that look like? So let's think about maybe patterning this one out. So I know, for example, that 5 cubed is 5 times 5 times 5. I know that 5 squared is 5 times 5. I know that 5 to the 1 is 5. I don't know why I put 2 here. This should be 5. And do you guys remember what 5 to the 0 should be? If you don't, you can kind of look at the pattern here. So as we move from here to here to here, the pattern is that we're always dividing by 5. So in other words, 5 times 5 times 5, that's 125. 5 squared is 25, so it's 125 divided by 5. To move from 25 to 5, we also have this pattern of dividing by 5. If I go up the rung, I'm multiplying by 5. And if I go down the rung of powers, I'm dividing by 5. So it's natural for us in this particular instance down here to take 5 divided by 5 and get the number 1. So this is typically how we define a 0 power kind of base. We define a 0 powered base to be equal to 1 based on this pattern that we see of dividing by 5. And then we can keep going. We can go, okay, well, what do we want to interpret 5 to the negative 1 as? Well, I want to keep this pattern of division by 5 going. So we get 1 divided by 5. Okay, or we can also write this as 1/5. And if I keep this pattern going, we'll keep this going to maybe 5 to the minus 3. I just keep dividing by 5. If you take your calculator and do 1/5 divided by 5, actually, I actually have my calculator right here. Well, maybe not. Where's that calculator? Oh, there it is. So I'm just going to pop up the calculator. I'm going to throw in a fraction of a 1/5. And then I'm going to tell the calculator to divide this by 5. I want to continue the pattern of division by 5. And I get 1/25. And hopefully that's not like a super surprising thing to see. And actually it's really interesting because 5 to the negative 2 is very similar to 5 to the 2, right? 5 squared is 25. And 5 to the negative 2 is 1/25. What do you think 5 to the negative 3 is? Well, my guess is that maybe this is going to be somehow related to 5 cubed. Let's take our 1/25, which is 5 to the minus 2, and let's divide by 5. Interesting. So instead of having the 25 or the 125 in the numerator, right, as a whole number, we're getting the 25s and the 125s as part of the denominator. So typically what we do for this expression, a number to the negative power, we usually say that this is equivalent to a fraction, where in the numerator we have 1, and in the denominator we have that same number, but to a positive power instead. Because I can think about, for example, I can think about this one as 1/5 times 5 times 5. Or I can think about 1/25 as 1/5 times 5, right? So 1 over that base with the corresponding positive power. I'm good for now, thank you. So maybe just a couple numerical examples here just to make sure we're all on the same page. What if we had 7 to the negative 3? How could we interpret that? Or, I mean, we could be working with integers as well. We could be working with something like negative 2 to the, I don't know, negative 3. How do we interpret these numbers? So 7 to the negative 3, we interpret this as a fraction, where the numerator is 1, and the denominator is the same base, but we have a positive power instead. So this is really like 1/7 times 7 times 7. I'm not exactly sure what 7 times 7 times 7 is. 343. So that's how we want to interpret this, and we interpret it in this way so that it follows this pattern of multiplication and division by 7, like the same thing we did for the number 5 up here. Okay, if I could have an integer, so I could have something like negative 2 to the power of negative 3. How do I interpret this? Well, I interpret this again as a fraction, where there's a 1 in the numerator, and I keep the base, so negative 2 is the base. I keep the base, but I make the power a positive power. So now I'm thinking about this as 1/2 times negative 2 times negative 2. Okay, 2 times 2 times 2 is 8, but we have a negative times a negative, which is a positive, times another negative, which is a negative. So we should get -8 in the denominator. Okay, so that's how we interpret negative 2 to the power of negative 3. We get -1/8. So that is a little ditty about negative powers. That was number 6. And of course, we talked about number 7. I think this is going to be our last property, and that is that a to the power of 0 is equal to 1, provided, excuse me, A lot of talking today, apparently. So a to the power of 0 is 1, provided that the base is not 0. Now, if a happens to be equal to 0, 0 to the 0 is technically an indeterminate kind of statement. And we've talked about indeterminate before. Indeterminate is an expression that we used for 0 divided by 0 as well. And we used that expression because 0 divided by 0 could technically be anything that it wanted to be, and you kind of needed a little bit more context in order to define this as a number, right? We can't, without a bit more info, it's hard to figure out what that number looks like. And 0 to the 0 has that property as well. I would say that about 95% of the time where 0 to the power of 0 is involved, we typically do get the number 1. So you might see online, for example, that a lot of people are just like, let it be 1, who the F cares, whatever, deal with your problems, bro. But, you know, from a mathematical standpoint, I don't think that's the right way to approach this. I think the right way is to say, you know, there are some cases where 0 to the power of 0 may not be 1. So I would say probably don't want, and I think if, to be honest, I think if we try to do this in our calculator, the calculator may yell at us. I don't know. It's been a while since I've done this on a calculator. So yeah, the calculator definitely tells me this is a math error, which in our case, we're going to interpret it as indeterminate. 0 to the 0 is not undefined per se. Like, we can define it as something, we just don't know how to define it. So most of the time we could define it as the number 1 based on the calculus problem that's involved, but every once in a while 0 to the 0 may not be 1. So that's why I kind of err on the side of caution here and just say, well, let's just make students not evaluate this kind of thing, or know that it's one of those odd cases like 0 divided by 0. Okay, I think that is most of the properties that I wanted to chat about. Oh, maybe it's worthwhile for us to chat about why exponentiation does not distribute over addition. So this will come up a bit if you're teaching students and they're just starting to learn about dealing with exponents. You're going to, of course, come across questions that look something like this. It usually happens inside of like the algebra. I'm going to actually make this I'm going to swap these numbers so it's a little bit easier. It usually happens inside the algebra part where students are going to want to rewrite this. So they want to write x squared plus 4 squared or x squared plus 16, but that's not right. And we can probably explain why this doesn't work with a numerical example. That's probably sufficient for most middle grade students to see. So let's look at a numerical example. And let's do something like, I don't know, 3 plus 4 squared. And we're going to evaluate this in 2 ways. We're going to evaluate this the right way using the order of operations. Okay, so in other words, we're going to look at PEMDAS. We're going to look at tier 1, which is working in the parentheses first. If I work in the parentheses first, 3 plus 4 is 7. So I'm going to get 7 squared, and I know that 7 squared is 49. Okay, so this is the correct way using the order of operations agreement that we talked about in Wednesday's class. Now, let's go back and let's assume that we can distribute the square through the bracket. So we can distribute exponentiation across addition. I don't know. Okay, so assuming that we can distribute this 2 over the addition, we would get something like 3 squared plus 4 squared. We know that 3 squared is 9, and 4 squared is 16. And when I add 9 and 16, we actually get 25. So what happens is these don't match. These are not the same. Okay, so something's up here, something's not quite right. Using the order of operation gives us one thing. Assuming we've made an assumption here that we can distribute over the addition, that gives us something else. So usually when we assume something and we get an answer that doesn't match up with something that we know should be true, it means our assumption is wrong. So that means that our assumption that we can distribute over addition has to be wrong. That's the logic here. So the right-hand side of this page is actually an incorrect way of evaluating this particular problem. Okay, so hopefully that's a numerical example of why that is the case. If you need to, we know that this is correct, right? Because we talked about the order of operations agreement. Parentheses have to come first, so our final answer we're expecting is 49. On the right-hand side here, is incorrect because we've made an assumption, and that assumption is not true. Okay, so that is most of the properties that I would like to chat about. I think we have seen most of the stuff. So I think what I would like to do is just work through potentially a couple kind of larger style simplification problems, because I usually like to have some kind of simplification problem on the final exam because it's kind of straightforward and just reminds me that I can let you out into the world, the big wide world of mathematics. Because for the most part, I would say that working with integers and working with fractions, that's going to be the hardest part, I think, of what you might ever have to teach at the elementary and middle school level, right? You might eventually start working into algebra, but most of you are probably not geared towards high school, so you're probably not going to have to deal with a lot of algebra at your level. So I want to be confident that you're happy with the mathematics that you're most likely to see. Okay, so let's go ahead and simplify this expression. And then we'll do maybe a nice little, yeah, that looks good. Do that one at the end. Okay, so we have an expression here. In the numerator, we have 5 to the negative 2 times 2 to the negative 5 times 5 to the negative 2. So a little kind of swapsies there with the bases and the powers. In the denominator, we have 2 squared times 5 to the negative 1. All of that's in brackets and raised to the power of 3. So we want to make a game plan. And usually my game plan is to kind of work on the numerator, work on the denominator separately, and then you kind of combine them and try to finish off the question. Because with these kinds of questions, I find it's quite easy to get lost in here and not know where to go. So my recommendation is, if you're not super comfortable, start by working with just the numerator. Is there anything inside the numerator? So is there anything up here that we could maybe commute? And are there any properties of exponents that we can use up here inside the numerator? So hopefully you notice that there's a 5 and a 5. right, as bases. So we could rewrite the numerator in the following way. I'm going to leave the denominator for now. We'll deal with it after. And so my focus is going to be on getting these 5s together, right? So I can definitely combine these 5s. This is going to be 5 to the negative 2 plus negative 2. Because I'm multiplying like bases, I'm going to add those integers together. Be careful, this is an addition of integers. And we know from our discussion about integers, negative 2, so I'm going to do this maybe in green over on the side, negative 2 plus negative 2 is really like negative 2 take away 2 more, which is really like negative 4. So the new power of 5 in the numerator should be 5 to the negative 4. Now, that's really all I can do in the numerator because now I have different bases. I have a base of 5, I have a base of 2. There's no way that I can somehow crossbreed these bases. It just does. I can't make a mule out of these things. It's not going to work. So 5s and 2s, they're different prime numbers. They're kind of stuck in their own little world. So our focus now turns to the denominator. Sorry, I might have to... Okay, we're good. Thought I had to sneeze a little bit there, but we're good. So in the denominator, I don't have like bases that I can multiply, but maybe you notice that we have a base that's raised to a power. So I'm just going to circle that base. We have a base that's raised to the power of 3. So what I want to do is I want to distribute the power through the multiplication. So that's my goal next, is to distribute that power through the multiplication. So we're going to get 2 to the 2 times 3. And we're going to get 5 to the negative 1 times 3. Okay, so distributing that 3 across the multiplication. And then let's just multiply these integers down here at the bottom. So 2 to the 6, and we have 5 to the negative 3. And what I'm going to do is I'm actually just going to swap the order of these things so that the 5s are kind of in the same column here, and that the 2s are in the same column as well. Because now that I've simplified the numerator fully and I've simplified the denominator fully, I can now start looking at these columns. So in red, I can look at these and go, oh, okay, I now have a division of like bases. Let's subtract those powers. And similarly with the 2s, I have a division of like bases. Let's try to subtract those powers. Okay, so for 5, we get negative 4 minus negative 3. Again, be careful. This is a subtraction of integers. And we're going to get 2 to the negative 5 minus 6. If you need to, do a little scratch work over on the side, right? We have negative 4 take away negative 3, which we know should be negative 4 plus 3. Or if it's easier for you to think, we can commute these and go 3 take away 4. So since 4 is the larger of the two numbers, we should get 5 to the negative 1. Okay, and finally we have negative 5 take away 6 more, which is negative 11. So there's two ways we can do this. It really just depends on your personal preference. I'm fine with you leaving this as 2 to the minus 11, 5 to the minus 1. Or if you want, we could rewrite this with positive power. So I could push both of these down into the denominator if you wanted to. So we would get 2 to the 11 times 5 in the denominator. I think both of these are acceptable final answers without actually multiplying everything out and getting one gigantic fraction. And like I said, my preference is usually to leave it like this. But if you're working, in middle school, into those early high school years, I know that a lot of teachers kind of push for the ability for students to be able to convert this into a fraction. So it really just comes down to your personal preference and what you want your students to be focusing on. Okay, let's do one more example here. So this is kind of one of my favorite styles of questions. You basically get this really big mess of stuff, and I tell you that it can be simplified to look like 2 to the power of something times 5 to the power of something. Okay, so this big mess can be simplified, and it can be simplified quite nicely. And our end goal is to simplify it and try to figure out what's going to be the final power of the number 2 and what's going to be the final power of the number 5. So I'm going to go ahead, I'm just going to maybe just copy this, and we're just going to paste this down here. Okay, and that way we can kind of start working away at this when you're ready. So pause the video if you need to copy some stuff down. I'm just going to take a little sip of water and start having at it. Okay, remember the process of attack. Let's start with the numerator first. Let's try to simplify this numerator into 2's and 5's the best we can. I am going to start, I think, right here by using the multiplication property. So I'm going to get something like 10 to the negative 2 times 5 to the 6 times 2 to the negative 3 times 2. So I'm going to multiply these two numbers together. And actually, maybe I'll leave my highlights here too, so you can kind of see what we are breaking down. Okay, negative 3 times 2 is negative 6. Now, it pretty much looks like the numerator is pretty good, but I know that my final answer has to be 2's and 5's only. So this 10 to the negative 2 is a little bit of an issue here because it's not broken down into 2's and 5's yet. But we know that 10 is equal to 2 times 5. So 10 to the negative 2 should be 2 times 5 to the negative 2. So I'm going to go ahead and I'm going to rewrite that. And then our goal is going to be to, again, distribute, like we were doing in the last question. We want to distribute this minus 2 over that multiplication of 2 and 5. Okay, so distributing this negative 2 through, we get 2 to the negative 2 times 5 to the negative 2 plus, times the rest. And now we're in pretty good shape in the numerator. I'm going to go ahead, I'm going to look at the 2's that I have, I'm going to look at the 5's that I have, and I'm going to try to combine these using the addition property of exponents. So similar bases means that we add together, and again it's addition of integers, so be very careful here. Okay, so 2 to the negative 2 plus negative 6, and then 5 to the negative 2 plus 6. Okay, so still haven't touched that denominator yet, right? My goal is just to work on the numerator first, so I have a very definitive kind of game plan to follow here. Okay, over on the side, let's look at negative 2 plus negative 6. This is really like negative 2 minus 6 more, so this should be negative 8. Then we have negative 2 plus 6, which I like to commute this and think about it as 6 minus 2, which is 4. and that takes care of the numerator. Right, so now you notice in the numerator, I'm just going to highlight it in the numerator, we have a base of 2, a base of 5. These are both prime numbers, so there's no way that I can somehow manage to combine these things using exponent laws. So our goal now turns to dealing with the denominator, and first and foremost, let's distribute this minus 3 over this multiplication. So let's see, we're going to get 2 to the negative 1 times negative 3. So remember, this is a base raised to a power, so I have to multiply these powers together. Okay, 5's a little bit easier to deal with. I just get 5 to the negative 3. And so simplifying, we're going to get something that looks like this. 20 squared, we're going to have 2 to the negative 1 times negative 3. All right, we're in pretty good shape. The last step here is just to deal with the number 20. So the number 20 is composed of 2's and 5's. So let's do a little quick prime factorization of that one. We know 20 is 4 times 5, or 2 times 2 times 5. Okay, so if we know that 20 is 2 times 2 times 5, then 20 squared should be 2 times 2 times 5 squared. And I keep kind of bouncing back and forth between multiplication symbols and dots. They are the same thing, by the way. Okay, let's go ahead and maybe focus now on distributing this squared through the brackets. And then we're almost done finishing up this question here. And like I said before, I'm doing this in a very kind of methodical way and trying to write out most of my steps. So yes, it is going to be a little bit of writing, but hopefully when you go back and look at stuff, you're going to be like, oh, right, so that's the rule that we used. Because I find also, too, that we get really comfortable sometimes teaching exponents, and we kind of forget that students need to see some of those steps written out very explicitly. So the last step in the denominator is just to take a look at your 2's, take a look at your 5's, and combine all of those powers together using addition. So I'm going to combine all of my 2's together. I have 2 plus 2 plus 3. And the 5's, we have a 2 plus negative 3. Okay, 2, that's 4, that's 7, so 2 to the 7. And we have 2 minus 3, which is negative 1. Awesome. Pretty much there, and like we were doing in the last example, we're just going to kind of compare now across the division symbol and think about this as a subtraction of powers. So comparing my like bases, we'll get 2 to the negative 8 minus 7, and we're going to get 5 to the 4 minus negative 1. So again, be careful, this is a subtraction of integers. So 4 minus negative 1 here. Negative 8 minus 7 is going to be minus 15. And then 4 take away negative 1 is really like 4 plus 1. So we're going to get 5 to the power of 5. So that's going to be our final answer that we're looking for. We're going to scroll back to the statement of the question. We wanted to find P and Q. P was the power of 2, and Q was the power of 5. So scrolling back down, we know that P is equal to negative 15, and Q is equal to 5. All right, so that's going to finish our little session about exponents, how to deal with exponent properties, interpreting things like negative exponents, and how to work with addition, subtraction, and multiplication of integers. That's really the goal of working with exponents, I think, with regards to using negative numbers in here. All right, so hopefully you guys have a lovely weekend. That's going to finish up our section on integers. And then I think, we're going to start moving into fractions and working a bit more with fractions here next week.